Welcome, everyone. Let's get started. As usual, there are office hours today right after class. And a reminder that the final 2 classes in the course are going to be this Wednesday and Thursday. Thursday, again, is special schedule because it is the last week of class for most courses, and it will be at the usual time on Thursday. Are there any questions? When will we know participation and attendance marks? I will be in touch about that at within like a week, I think. Reach out to Vincent about timing on the problem sets. Any more questions? Okay, let's get started. Oh, and actually, just as a preview of what we're going to be doing this week, we're going to be having this class and the next class will be on neural networks. And then on Thursday, we're going to finish by seeing some things that are just cool from around math. We're going to look at some unsolved problems, and we're going to look at some paradoxes, things that seem to be paradoxes. So that will be the last couple of classes. So, review of the gradient. If one has a multivariable function, we can write it as a function literally of multiple variables, or one can write it as f of x, where x is a vector. So if one has this multivariate function, one can write down the gradient of the function as just the vector of partial derivatives with respect to the individual variables. So this is the gradient of the function. It's just the vector where the first part is the derivative of f with respect to the first variable, then all the way to the derivative of f with respect to the nth variable. This is assuming that the function has a single variable output. So an example of such a function might be you just sum all the entries of the vector together. So that would take in a vector and give you out a scalar. So if you take in a vector and get out a scalar, then you can take the gradient of the function and you get a vector. So as we saw before, we can use the gradient to estimate the amount that f is changing. So if we add a little bit to the input vector x, if we add epsilon1 to x1 all the way up to epsilon n to xn, then we can approximate the function at this new point by taking the function at the old point and by taking the gradient and dotting it with the epsilon. So if we move a little bit away, it's like doing it's a first order approximation, and we'll see the analog again with the single variable approximation. But yeah, so if we move a little bit in one direction, we can use the gradient to work it out. So that means that the dot product, this particular dot product, is going to be maximized when the vectors are aligned. So if we're trying to increase the function and trying to push the function to increase it, we're going to point along the gradient. We should have this be pointing in the same direction as the gradient. And if we want to decrease the function, we want to have the vector of epsilons pointing in the direction of the negative gradient. And so this is the idea behind what we're going to see now, which is gradient descent, which is an algorithm to find the minimum of functions. Doesn't always work, sometimes works. So the basic idea here is that you take a starting point and you will take various steps. It looks sort of continuous here, but I guess even in this picture, it is actually, there are various steps going on. They're just small, hard to see steps. You take a step in the direction of the gradient, so you're decreasing your function. You take another step, decreasing your function. Now, the directions you're going to have to go in change depending upon where you are. So what the direction is that you need to go in over here is different from the direction you need to go in over here. You can see that you start out going in this direction, then you go in this direction, and you sort of meander a bit depending upon where you are. This is like the greedy approach, basically, to finding a minimum. You're like, where can I go down the most? I'm going to go in that direction. I'm going to take a small step in that direction. I'm going to keep on doing that. We'll just make that formal in a moment, but for the moment, are there any questions? Okay. So in gradient descent, we're going to use this property of the gradient that you can use it sort of to approximate the direction where you go down the most to our benefit to find the minimum. So starting at some point, again, this is a vector x0. I'm just using a superscript because subscripts I'm using for the entries of a vector. X0 is just a vector, x1 is a vector, x2 is a vector, and so on. So starting at some point, x0 in R to the n, a vector, we progressively will find points by updating the point that we're at. We will take the point that we were at, compute the gradient at that point. So remember, the gradient is a function. So going back here, the gradient is the derivatives of the function with respect to the individual variables. So just like any derivative, it is itself a function. So for example, if my function is x squared, its derivative is 2x, which means that I can evaluate the derivative at any point. So in the same way, I can evaluate the gradient at any point, and I will get a different answer. So the gradient here is going to point in this direction, the gradient here is going to point in this direction, and so on. So what I'm doing here is I'm saying, let me take a point, let me take the gradient at that point, evaluate it at that point, and then I'm going to take the point minus the gradient, and this is just some constant that I'm throwing in there, which is a learning rate, and that basically scales down the gradient, and we'll see why that's the case in a moment. Typically, it's something small, so it's a fixed learning rate, and again, this is just denoting the gradient of f evaluated at x to the k. At xk, the vector xk. So if gamma is very small, if our learning rate is small, we can use this approximation where f of xk plus 1, the next step in our path, is going to be equal to just this, because that's how we set xk plus 1. And we can write this with the approximation given by the gradient. We can say, since we were moving a little bit, we can treat this as our epsilon perturbation. And we can say it's very similar to if we had evaluated the function at the starting point, and then take the gradient dotted with the amount which we perturbed it. So that is going to be equal to this. So this is an approximation to what we're doing. And you see we're decreasing the function by the amount of the gradient, the norm of the gradient. And the key point here is, because we moved in the direction of the gradient, taking a step in that direction is the direction that decreases the function the most. So we're taking the right direction of step. We could have gone in another direction and maybe decreased the function, but this is maximally decreasing the function for a certain step size. And then the idea here is that we converge eventually to a minimum. Now, I am going to unpack several things here. First of all, there's a question. Is it part of the definition of gradient descent that gamma is fixed? Don't quote me on this. There are versions of gradient descent where you change the learning rate, and I will mention that a little bit later. There are lots of different versions of gradient descent. This is just sort of a basic version of gradient descent. But yes, good question. A question of re-explaining the perturbation and approximation here. Yes, absolutely. So I was going to do that. Let's go over here again. So this is, and we're going to see this in a different way in a, whoops, sorry, that was my connection. We're going to see this in a different way in a few slides. Can you hear me okay? My connection seems to be weird. Somebody post if you can hear me. Okay, good. Yeah, thanks. So this is the approximation that the way that the gradient helps us to do a first order approximation. We say, suppose that we moved each one of our coordinates by this little amount. So we're taking our vector x, x1 through xn, and we're moving it by a vector epsilon, epsilon1 through epsilon n. And in order to get the new value of the function here, an approximation is to take the value at x and I'm really sorry for the flickering screen. I don't know if that's coming through for you. I don't know what's causing it. I'm really sorry. And to take the function at x to add the gradient dotted with the perturbation. And we proved this a number of lectures ago, where, again, you take, in order to approximate the function at the new point, you take the function at the old point, and you add the gradient dotted with the perturbation. So that's what we're doing here. We're saying, since we're perturbing our original point xk by this small step that we're taking, we can write the new function as approximately, it's just an approximation, the function at the old point plus the gradient dotted with, and this is our epsilon. This is our perturbation. It's this thing that we're adding. And this thing happens to be the gradient as well. So it's the gradient dotted with the gradient. But that's just because we chose this kind of perturbation very carefully. Is that clear? Please let me know if there's something I should clarify more. Yeah, and this is going to be a good approximation exactly when this thing is very small. So either the gradient is small or you've taken a very small learning rate. Step size. More general, I think I'm using sort of deep learning language to think of learning rates. You could think of this as a step size. Probably step size is a more classic way to refer to it. So we repeat until we converge to a minimum, i.e. the steps become really small. So the steps are small if this is really small, right? Like we're taking a small step if the gradient has norm close to 0. But remember that when the gradient has norm close to 0, that's just like having the derivative be 0. The derivative of something is 0 if you are at an optimum, a local optimum, or if you're at a saddle point. But we're going to, assuming, first order, we're assuming that, once you've reached the minimum, that's when your gradients go to 0. That means that your step sizes are getting smaller and smaller and smaller. So you have reached a sort of an equilibrium point. You stop moving very much in your steps. And if your steps become really, really small, you say, OK, I'm close enough. Done. You never actually reach it, but you get closer and closer and closer. So this is not one of those algorithms that terminates at an exact point. It's an algorithm that terminates when you say, oh, I'm good enough. There is a question about a larger learning rate. We will get to that. You don't want a larger learning rate. There's a question about higher order derivatives. We will also get to that. We're not going to get to better approximations. There are better approximations to gradient descent that use higher order derivatives. We're not going to look at that. There are, for example, in deep learning methods that try to approximate this, but basically the reason why you wouldn't do that is just because it's computationally intensive to compute higher order derivatives, because the version of the gradient, which we'll get to in a few slides, for, say, second derivatives is called the Hessian, and it's a matrix. And so if you're working in n dimensions, if n is large, instead of having to compute the gradient, which is a single length n vector, you're going to have to compute an n by n matrix, which is computationally intensive. OK, so I should mention there is also something you can do similarly, which is gradient ascent, to find the maximum, where instead of going down the gradient, you go up the gradient and you take the step just in reverse. And that will hopefully get you to a maximum. Are there questions? And we'll get in a moment to when this doesn't work. OK. So this is, again, the way we're doing gradient descent. We're taking these steps, we're updating our vector, and we're hopefully reaching a minimum. What are some ways that this can fail? There are several of them. And I'm going to assume that we are working with differentiable functions so that this is actually defined, but that's a very fair point. If this is literally not defined, then you're in big trouble. Great, there are so many problems. So let's go through a few of these. There are essentially three ways, and tell me if I missed anything. There are essentially three ways that gradient descent can fail. First is we have an iterative algorithm. It could converge, but it could converge to the wrong point. You could end up in a place that's not actually the minimum. We'll go through each of these individually. Second is the algorithm just doesn't converge. I guess so this is just like three ways that generically an iterative algorithm that's supposed to converge to something could just not work. The first thing is that the algorithm doesn't converge to the right point. It converges, it doesn't converge to the right point. The second is that it just doesn't converge at all. You never reach a point that converges. And then the third is that it does converge, but it does so slowly that you're really frustrated. Maybe that's not a failure, but it's certainly like, it feels like a failure. So those are just three ways that an algorithm that's supposed to converge could fail. Now let's see when those happen for gradient descent specifically. So if it converges to the wrong point, that's a local minimum. So when do you find a local minimum? And what is a local minimum? And we can remember this from previous pictures that we looked at with single variable functions. And in general, this is the case with multivariate functions too. You could end up in a place where the gradients are 0 because you are at a local minimum. You can't go down without sort of going over to some other part of the function. And a local minimum is just a place where the gradient is 0, and locally around it, the function is bigger than it is right there. It's pretty clear that gradient descent is going to get stuck, because when you're close to here, there's no way for the gradient to know about this better minimum over here. You're just going to converge gradually to this point, get closer and closer and closer to it, and you'll say, this is the minimum. And you will be wrong. OK, so that's the first problem. Second problem is if the algorithm doesn't converge. And there are a couple of reasons why this might happen for gradient descent. The first one is sort of the stupid one, which is just there isn't a minimum. Which I guess maybe in some sense that's not failing, but if the function just isn't bounded, you could just descend forever. So imagine this is this big function where you just could keep on taking steps down and there's no bottom. You never hit bottom. Then you could also imagine that you have too large a learning rate. And so this is a bit more subtle and it's a bit more specific to gradient descent, where if you're taking these steps. Now, this step, if this is very big, you are basically just going in a random direction really far. So if you are here, you would really like to take a small step down here. Small step, small step, small step, small step, small step here. But if you went too far, if you took gamma to be too big, then you could say, I need to go in this direction. I know I need to go in this direction. Why didn't I go a lot in this direction? I'm going to go this far in this direction. Oh, shoot, I went too far. That's OK. I'm going to go really far in the other direction to make up for it. I'm going to go this far. And then you could actually end up getting out of you could go away from the minimum if you were taking too large a step size. So this is a problem with gradient descent. What you would like to do is you'd like have like really, really small step sizes. And the reason why you wouldn't maybe always do that is you also want to do it in a reasonable amount of time. So you would like to have as few steps as possible, but you would like to make sure that they're not too big. And this is sort of an entire area of work, but suffice it to say that this is a legit problem. People would really like to know exactly how large they can take their learning rates, gamma, before you start escaping the minima instead of falling into the minima. Yeah. If you train neural networks, this is often something that you run across, just everything nans if your learning rate's too high. There are questions. Is there a way to do a sort of curvature-aware gradient descent to ensure convergence to a global minimum? So there are absolutely curvature-aware gradient descents. If you are in deep learning, that is what things like Atom are trying to do. And optimizers that are more effective than just straight gradient descent. We're not going to get into Atom, but yes. Curvature is like higher order derivatives. So it is like you would be working with higher order derivatives. It's just things like Atom try to approximate the higher order derivatives because they don't want to actually compute them because they're super time intensive to compute. OK. More questions. In addition to local minimum, for deep learning settings where you would care about generalization, there's the wrong point. You could also be choosing one of several different global minima, one that doesn't generalize well. That is absolutely true. And hopefully we'll get to that next time. Right now, we're just trying to find one of the global minima for not thinking about the sort of interpretation of this to generalization. OK. And so finally, there's the third thing. The algorithm converges, but very slowly. And so what happens? What is the interpretation of this from a gradient descent perspective? Well, this is a flat region. Is basically some people think of these as saddle points, but there are like a number of situations where the gradient is just flat. Like you have a gradient that is very close to 0, or maybe exactly 0, and you can't get out of it, even though there is a place where you would really like to go. So here you imagine that there is this big, deep minimum here. I guess a little local minimum here. But you are over here. And the function is super flat. So you would like to move in this direction. And your gradient maybe is like slightly in this direction, but it's really, really small. And so you don't have enough oomph to get over to the local minimum until you've taken a really large number of steps. And this does happen in practice a lot, where you are technically making progress, but you're making progress so slowly that it's really bad. And this is really frustrating, especially if you theoretically could have been, like if you've been closer to the minimum, you would have found it really fast. OK. So how do you prevent these various failures? So the first one, this unbounded function thing, we're just going to generally assume we're working with bounded functions. If you're trying to find the minimum, you hope that there is actually a minimum. It's not too bad if you just keep on minimizing something and it just goes off to infinity. That just shows that the minimum was negative infinity. For the large learning rate, we can pick a low learning rate. Another thing that people might do is decrease it as they go. You could decrease the learning rate so that, and this actually has to do with the, there's an interpretation of this like temperature, where you start out having really large steps because you're trying to escape local minima, and you're like, I'm going to take big step, big step, big step, and then I'm going to gradually decrease the sizes of my steps, and I hope that because I took a lot of big steps, I'm going to have ended up in the big minimum rather than in one of these little minima. And so hopefully I'm going to be here, and then when I decrease my step size, I will gradually converge and stop bouncing down. So why this is a temperature interpretation is because you can think of this as being like a molecule of a gas that's bouncing around really fast, and then as you decrease the temperature, it bounces around more slowly, and it finally settles into a nice sort of stable state. You can look up simulated annealing if you're curious about algorithms like that. Are there cases where you want to start with a low learning rate and then increase it before decreasing it again? Maybe, I'm not sure. Where does vanishing or exploding gradients fall into the 3? So that would be a situation where so the algorithm converges but very slowly if the gradients are vanishing. So if things are really small, and the algorithm doesn't converge if the gradients are exploding. So they would fall under those two, and we will hopefully get to that next time, or yeah, we will hopefully get to that next time. But that's sort of a deep learning particular problem, vanishing and exploding gradients, or at least that language is. Is there no backtracking here? If you ended up in a worse minimum, could you go back to where you were? Sure, but you probably wouldn't have found your way all the way into the minimum. But yes, you could just like reinitialize your algorithm and see if you found a better minimum. But with this decreasing the learning rate thing, you probably wouldn't actually converge to the minimum until you've gone for a while, and so until the end. So you'd only reach one minimum. The final thing you reach is the only minimum that you ever find. Because if you actually settle in a minimum, you're never going to leave it, because gradient descent never gives you a signal to leave. Okay, flat regions. So we've looked at how you can deal with this. You just sort of don't worry about it. This, you do worry about it, and sometimes it works. Flat regions, it really is a problem, as we will see later. And then finally, local minima. So we can ignore local minima if the function is convex. Now, we're going to look at this, but for everybody who does deep learning is not convex optimization. I'm covering this because a lot of problems actually are convex optimization. Convex optimization is great, and in many situations it is super useful, and you can just use gradient descent. So in many situations, we've seen linear programming, there's convex programming where you have like nice convex programs where you can use variations of gradient descent to find your global optimum. So we can ignore local minima if the function is convex. Let's look at that. Let's look at what it means for a function to be convex, because we've seen functions being convex, but we've seen functions being convex from the perspective of univariate, single variable functions. So let's see what about multivariate functions. So convex functions. We saw previously that we defined a function to be convex if the second derivative was always greater than or equal to 0. Great. And then we could do things like, say, OK, the function looks like this, and you can apply Jensen's inequality, which we really like. Now, what does it mean for a multivariate function to be convex? So it takes in a vector as input, and it gives you out a scalar as output. What could it mean for a multivariate function to be convex? OK, So we're going to take a look at a couple of different interpretations here. As always with math, there are several ways of thinking about it. So here's the first way. One way is to use the graph. So remember, we thought of convexity sort of like convex. Well, concave is like it's like a cave. Convex is the opposite. It's like you flip it and it becomes a cave. But like the point there is that convex, if you take 2 points and you connect them and you are always above the graph. So if you take 2 points, 2 inputs to your function, the segment between the graph of one and the graph of the other never goes below the graph. So here is the way to see that. This is a generalization of the notion of convexity for univariate functions. You take a point and another point on the graph, and the entire segment between them is always above the graph. And that just means any point, if you take any t between 0 and 1, you can take the point, which is sort of 1/10 of the way, or fraction t way along this segment. You say, what's the combination of what is the point in between here? Well, the point in between here is t fx plus 1 minus t f of y. That's this point. And we want it to be greater than or equal to the point on the graph, which is function of tx plus 1 minus t y. This is essentially Jensen's inequality. So this is sort of the Jensen's inequality way to define convexity. And it's also the way that we defined a convex set. So if you think about a convex set, it was like any 2 points, the segment is completely contained between them. In a graph, it's like any 2 points on the graph, the segment is completely contained in the region above the graph. So again, a convex set and a convex graph, they're exactly the same thing because of Jensen's inequality. And this is just like Jensen's inequality. And now we've just said, okay, we didn't have to worry about these x's being univariate. They could just be vectors. You could imagine taking a graph. It's harder to visualize, but you take your graph, which is 3 dimensions because it's a function of 2 input variables, and you say you take your surface here. It looks like this. It's like a bowl, and the bowl is convex because you take any 2 points on the bowl, and the segment between the 2 points is completely above the bowl. Okay, so that's the definition of convexity that sort of generalizes the one we saw before. And then we're going to see another one which generalizes the other notion of convexity we saw before, because there was the second derivative test for convexity. But first, I guess, are there any questions about this? There's just one notion of convexity, just looking at the segment between any 2 points, saying it's above the graph. Is convexity defined for an interval? Yeah, you could say it's convex on this interval. Instead, you could say it's convex everywhere, or you could say it's convex in this particular interval or in this particular region. But this interval is just saying if you're picking any point on this segment, t equals 0 means you're all the way to this end of the segment, t equals 1 means you're all the way to this end of the segment. And this is just to say for any segment, all the points on the segment are above the graph. Okay. So another way to define convexity is to use the Hessian, as some people were saying. So let's look at what this Hessian is. So since we have a vector, we can't just write the second derivative is greater than 0, or it wouldn't be it wouldn't really mean anything. What is the second derivative of a function of many input variables? We have to consider derivatives with respect to all of the input variables. Now, with the gradient, we said, okay, we can take the derivative of f with respect to each one of the input variables, and that was enough. That was a vector. We got essentially all the first order derivatives that way. Now, for the second order derivatives, it's a bit more complicated. because you could take the derivative of x1 and then x1, and that would be like a second derivative. You could also take the derivative with respect to x1 and then the derivative with respect to x2, and that would be another second derivative. You take the derivative of x2 with respect to xn, that would be another one. You have a lot of them. You have actually n squared different ways to take the second derivative. And so you could express that as a matrix that captures all the possible ways to write the second derivatives. So this is the Hessian matrix. It is scary, but not actually too bad. It's just taking the second derivative with respect to, in this case, it's with respect to 1 and 1. Second derivative with respect to 1 and then 2. Second derivative with respect to 1 and then n, and so on. It's going to be symmetric because it doesn't matter the order in which you take second derivatives. We didn't actually show that, but that is a thing. So this is going to be the same as this. Question, what is a Jacobian? So we saw that very briefly in a previous lecture, that the Jacobian is what happens if you take a vector-valued function and you take the derivative of it with respect to all of the, a function of vectors to vectors. And then you can take the derivative of the final output vector with respect to the input vector. And that's also going to give you a matrix, but it is a first order derivative. It's just what happens if you take the derivative of this output entry with respect to this input entry. The Jacobian is just the gradient if the output has just one dimension. So we are in the situation where the output has one dimension, the input has many dimensions, and so the first derivative is the gradient, which is just a vector, and the second derivative is the Hessian, which is a matrix, two-dimensional. Good question. I used to get those confused. More questions. Is the Hessian the Jacobian of the derivative? Yes. Laplacians are something different. Okay, let's move on. Let's see in particular how we can use that. Didn't just write this down for fun. So it is pretty fun. So we saw that we could do a first order linear approximation of just univariate functions. If your input to your function is just univariate, then we have this. This is the first order Taylor approximation, remember? This is just like starting a Taylor series. So the 0th order Taylor approximation is just, suppose you move a little bit. Well, f of x plus epsilon is basically f of x. That's the 0th order approximation. The first order approximation is you add epsilon times f prime of x, a derivative at x. That's the first order linear approximation of f of x plus epsilon. And then if you wanted to do the quadratic approximation, so the second order approximation, you would do this. Sorry, this should be a squared. There should be a squared here. So this is just the second order Taylor polynomial, basically. Again, sorry, there should be a squared there. This is the second degree Taylor polynomial. So if you were to just keep on expanding out the Taylor polynomial, it would have like epsilon cubed over 3 factorial times the f triple prime, the third derivative, plus epsilon to the 4th time over 4 factorial times the 4th derivative of f. Again, this should be an epsilon squared, I'm sorry. Now, let's generalize this to higher dimensions. This was a univariate. This is like us going and doing Taylor series for vectors instead of for scalars. So suppose that we have now x as a vector. And that means that epsilon, our little change to x, our small perturbation, is also going to be a vector. So we actually already have the first order approximation, which generalizes this. And that's the thing that we saw with the gradient at the start of class today. F of x plus epsilon is approximately f of x plus epsilon dotted with the gradient. So it's just the same as this. Instead of epsilon times the derivative, it's now epsilon, which is a vector, dotted with the gradient, which is also a vector. And so the dot product is a scalar, and so we add that scalar to this scalar, and we get approximately the new value. Great, so that's the first order approximation of f of x plus epsilon. Now let's see what the second order approximation is. We haven't seen this before, and we're trying to make an analogy to this, where again, epsilon squared, sorry about that, epsilon squared over 2. What is the second order approximation? Or what is the new term here? Any guesses? Yes, there will be a Hessian involved. So we would be really tempted to do epsilon dot the Hessian. The problem with epsilon dot, or epsilon squared, sorry, dot the Hessian. The problem is epsilon squared, what's epsilon squared? Epsilon is now a vector. Also, you can't dot it with the Hessian because the Hessian isn't a vector, it's a matrix. But it's really close. So we want basically epsilon squared here. And we want over 2, and we want to multiply in the Hessian. So how do we do that? Well, we say epsilon's a vector. The Hessian is a matrix. Let's multiply epsilon on one side by the Hessian and multiply epsilon on the other side by the Hessian. This is called a quadratic form. What is the dimension of this? Well, this is an n by n matrix. You multiply it by an n by 1 vector, and you get an n by 1 vector. This is a 1 by n vector, and you get a 1 by n times an n by 1, which is just a 1 by 1 matrix, which is a scalar. So this is 1 by n times n by n times n by 1, and that gives you a scalar, which you can add to this scalar and this scalar to get this final scalar. So this is the second order approximation. It is just the analogy of this. Or again, it should be epsilon squared over 2 here, sorry. But here you have f of x, that lines up here. Here it's epsilon times the derivative. Here it's epsilon dotted with the derivative, or dotted with the gradient. And here it's just basically the equivalent of epsilon squared times the Hessian. But in order to make the dimensions line up, this is what you have to do. And you can prove it with some more algebra. You can prove it with some more algebra. This is exactly correct. I'm not going to go through the algebra. But it's similar to what we did with the gradient to show that the first order approximation with the gradient was valid. Yeah. Questions? We saw quadratic forms like this in one of the p-sets. Yes, we did. Funny you should mention that. So get right back to that. What's the analogous statement for f prime of x is greater than or equal to 0? That was the convex. That was the statement about f being convex if the second derivative of f is greater than or equal to 0. What is the analogous statement here now that we're in Hessian land? I remember people at the start were saying the Hessian has to be positive semi-definite. So yes, and why is that? Well, because remember from a past p-set that a matrix is positive semi-definite if every quadratic form with respect to it is, or positive semi-definite if every quadratic form with respect to it is non-negative. So the analogous statement to saying the second derivative is greater than or equal to 0 is for saying that for any vector epsilon, this thing is greater than or equal to 0. Because this is the same term as this. Again, this should be epsilon squared. So this is positive when the second derivative of f is positive. This is positive when this thing is positive. So if this is always positive, then the function is convex. When is this thing positive always? For every epsilon? Well, it's positive for every epsilon exactly when this is a positive semi-definite matrix. I guess it's non-negative for every epsilon, exactly when it's a positive semi-definite matrix. The term positive definite matrix is just if you don't allow it to be equal to 0, if you just say it's strictly greater than 0. And that corresponds to what's called strict convexity. But yeah, so a function is convex if the second derivative is greater than or equal to 0. But what is the second derivative greater than or equal to 0? What does that mean if you're in higher dimensions? Well, it just means that this quadratic form is always greater than or equal to 0 for any epsilon, which means that the matrix is positive semi-definite. So that's why, if you have heard that a higher dimensions function is convex if and only if the Hessian is positive semi-definite, this is why. It's literally the same thing as the single variable case. And there's another way that you can think about this, which we won't prove, but it's pretty doable to prove just because of time. Another way to define positive semi-definite is to say that all the eigenvalues are greater than or equal to 0. And one way to think about that is sort of pretty simple. If you imagine that you had an eigenvector that has an eigenvalue less than 0, well, what if you plugged in that eigenvector for epsilon? You would end up getting this Hessian times the eigenvector, which would be negative of the eigenvector, or negative, there would be eigenvalue times the eigenvector, dotted with the eigenvector again, which would be the eigenvalue. So this thing, or sorry, it would be yes, which you would end up getting just the eigenvalue for this quadratic form. And if the eigenvalue is negative, then this would be less than 0. If you didn't get that, don't worry. But this is just to say, this is another way of defining a positive semi-definite matrix to say all the eigenvalues are greater than or equal to 0. So you will sometimes see that as the expression for when a function is convex. Questions? OK. So let's finish for today by talking about gradient descent in convex functions, which is why we brought up gradient descent. So for a convex function, any local minimum is also a global minimum. So remember, there's this problem where we could be in a local minimum, and we could have a global minimum over here. Now, could this happen with a convex function? No, because suppose to towards contradiction, we have a convex function with a local minimum over here and a global minimum which is deeper than it. Then if you take the segment between them, clearly there have to be some points on the function above this segment. Why? Well, because x was a local minimum. And so right around x, everything went up. And so if you look at the segment, everything around x has to go up. So there had to have been a point above the segment. That's totally informal, but it's actually pretty close to a rigorous proof. So that is just saying that we used our first definition of convexity. So the first definition of convexity was every segment has to be above the graph of the function. You could also prove it from the second definition if you wanted to with the Hessian. Showing that if the Hessian is positive semi-definite, then every local minimum is also a global minimum. But yeah, in this case, you couldn't have f be convex. We have a contradiction because we have the segment which is supposed to be above the graph being actually below the graph. So the takeaway from this is if you're doing gradient descent with a convex function, you don't have to worry about falling into one of these local minima because the local minima are in fact global minima. And in this particular case, this is very much not a convex function because it's going up and down, and yeah, this is not a convex function. This is a non-convex function. Okay, I will stick around for questions, and then there will be office hours. We will finish up with neural networks next time. And then on Thursday, we will have our last class. Again, it's on Thursday at the usual time. And that last class will be finishing up the semester by looking at some cool unsolved problems across math and some paradoxes or apparent paradoxes. Here is a poll about the speed of class, and I will stick around for questions.